Okay, so today we look at the subtopic, okay, of heat, which will be latent heat. Okay, latent heat. Now, what is latent heat? Latent heat basically heat needed to change the state, okay, of a substance. That means the state of matter, okay, without the change in temperature. So heat needed to change, okay, the state of matter or phase change of a matter without the change in temperature. So now, so basically there will be two types of latent heat. One we call it latent heat of fusion, which is heat required to change from solid to liquid, or the other way around. Latent heat of vaporization is the heat required to change from liquid to gas, or the other way around. Okay, so now, so let's say if you have solid, okay, then liquid, then gas, right? Now, so so we have solid, okay, liquid, and gas. Okay, so from solid to liquid, and then liquid to gas. Okay, solid to liquid, and then liquid back to solid, liquid to gas, or gas back to liquid. Okay, so this one is actually solid to liquid is your melting process. Okay, so melting, and then liquid to gas is boiling. So gas back to liquid is condensation. Then liquid back to solid, okay, solidification. Okay, solidification, freezing solidification. So all these four processes involve the concept of latent heat. Okay, now the changes during melting or solidification, okay, we call it as latent heat of fusion. Okay, whereas the changes from liquid to gas, or the other way around, that means during boiling, condensation, that one we call it as latent heat of vaporization. Okay, now, so to understand the concept of latent heat, right, we look at the heating curve. So basically for the heating curve, okay, so we have the graph of temperature against time. So this time actually will represent your heat supply. Okay, so the time here will be heat supply. Okay, so what happens is, okay, so we start from solid. So solid. So when you increase, say, when you supply the heat, what happens, you see that the temperature will increase, and then up to the point here, BC, what happened? Melting happened. Okay, so melting lah. Okay, okay, melting. Now during melting, what happens is the matter will exist in two forms, solid and liquid. Okay, so the liquid, after that is 100% liquid. Okay, so this is liquid. Okay, liquid. Okay, then what happens is this one is boiling. Okay, boiling. So during boiling, what happened? The matter will exist in two forms, which is liquid and gas. Okay, liquid plus gas. Okay, so liquid and gas. So liquid and gas. Okay, and then this is 100% gas 100% gas. Okay, so you see that during solid, liquid, and gas, you see that when you supply the heat, the temperature increases. You supply the heat, temperature increases. You supply the heat, temperature increases. Why? Because during this time, right, the heat supply increases the kinetic energy Okay, kinetic energy of the material. Okay, so naphthalene is the material here Okay, so kinetic energy of the material So this one, naphthalene is the material we use. Okay, so it can be any other material okay, or any substance okay, any other substance we use also can. Okay, so the substance here, example, we take naphthalene okay, so kinetic energy increases when you supply the heat. So that's why I see the temperature increases okay, during solid, liquid, and gas. Okay, But during melting and boiling, you see there's no changes in temperature. Okay, so why during this time, okay, the heat is used to overcome the bonding forces between the molecules. That means the heat supplied is used to overcome the bonding forces between the molecules and not increase the kinetic energy. Okay, so the kinetic energy remains constant during the melting and boiling. So this is latent heat of fusion. This is latent heat of vaporization. Okay, latent heat of vaporization. Okay, same thing for the cooling curve. Okay, this one is gas. So what happened? The temperature decreases. After that, condensation happened. So during BC, you have the form in gas and liquid. And then after that, it's 100% liquid. The temperature decreases. And then what happened is during this part, okay, solidification happen. Solidification, that means it'll be in a liquid and solid. And then here will be 100% solid. Okay, same thing right here. What happened? You see the temperature decreases for gas, for liquid, for solid. Why? Because the kinetic energy decreases. Okay, but during what they call it, condensation and solidification, you see the temperature remains the same. Okay, because during this time the bonding happens. Okay, the bonding process happens. Okay. Okay, next we look at what is meant by specific latent heat of fusion. Now, specific latent heat of fusion is defined as heat required to change 1 kilogram of substance, right? Okay, from solid to liquid without change in temperature. So heat needed to change 1 kilogram of solid to liquid without change in temperature. So the 1 kilogram is important here. Okay, so the word specific, that means it's only specific for 1 kilogram. Okay, 1 kilogram. Now, whereas specific latent heat of vaporization is the heat required to change 1 kilogram of liquid to gas, or the other way around. Okay, at a constant temperature. So it's 1 kilogram of liquid to gas. Specific latent heat of vaporization. Now, the unit for both specific latent heat will be joule per kg. Okay, or joule kg minus 1. So if you bring down, it becomes joule over kg. Okay, so joule is the unit of heat. Okay, kg is the unit of mass. So mass is represented by m, heat is represented by q. So this is the unit of L. Okay, so from there you can get L equals to q over m. So when you cross multiply, you get q equals to ml. So basically, q is the heat needed, right, to change the state of matter. Okay, at any mass, So q equals ml. So m will be your mass, L will be your specific latent heat. Okay, whether fusion or vaporization. Okay, now, so we look at how to use this formula first. Now, calculate the quantity of heat required to melt. So you melt 2 kilogram of ice at 0 degrees Celsius. So this one just use Q equals to ml. Okay. Equals to 2 times 3.34 times 10 to the power of 5. Okay, so we get 6.68 times 10 to the power of 5 joule. So this is just a basic question. Now calculate the heat energy needed to increase the temperature of 2 kilogram of ice at 0 to water at 20. Specific heat capacity of water is 4.2 times 10 to the power 3. Specific latent heat of fusion is 3.34 times 10 to the power 5. Okay, now this one, right? Okay, the process is not like you have 0 degrees Celsius of ice. Okay, you want to change to 20 degrees Celsius of water. Okay, so this is not the process. So what we must do is we have 0 degrees Celsius of ice, right? Okay, so what happens is first we need to melt. So we need to melt the ice first so that it becomes 0 degrees Celsius water. Okay, 0 degrees Celsius, water. Okay, so we need to melt the ice first. Now, so after melting, what happens is, then only we can increase it to 20 degrees Celsius water. Okay, 20 degrees Celsius water. So that means, right, the first process is melting, then only increase the temperature. So we melt the ice, then we increase the temperature. Now, during the melting process, the heat required will be Q equals to ml. During the increase in temperature, that's where we're going to use Q equals to mc theta. So these are your total heat lah. Okay, the ml you have to plus with the mc theta. Okay, so that means it's ml plus mc theta. So the m will be 2, L will be 3.34 times 10 to the power of 5, and then 2 times, so the C is 4.2 times 10 to the power of 3, and then the change in temperature from 20, so it's 0 to 20, so it's 20 only lah. So from there you can get your answer. Okay. T times 1,800 plus times 10 5. Okay. So you get 836,000 joule. Okay. So this one you have to be careful. This one you cannot direct from 0 to 20 first. So you need to melt the ice and then only you need to increase the temperature. Okay. Now next we look at experiment to determine specific latent heat of fusion of ice. Now for this experiment, right? Okay. So we want to use the formula Q equals to ml. So L equals to Q over M. So what you must do is, okay, you have a heater here. Okay, so this Q will be the heat from heater lah. So Q will be heat from heater. Heat supplied by heater. Okay, and then M will be the mass of melted ice. Okay, M will be the mass of melted ice. So M will be the mass of melted ice. So you have a apparatus lah. You have a filter funnel filled with ice, beaker, okay, immersion heater connected to power supply. Okay, connected to the power supply. Now the thing is, okay, for this experiment, right, there'll be two set of apparatus. Okay, you see here the heater here is not connected to the heater. Now why? Because you see, this Q is the heat from heater, and then M is the mass of ice melted because of heat from the heater. So what happened, right? If you don't put the heater, so anyhow the ice will melt because heat from surrounding. So the heat from surrounding will melt the ice. Okay, so the heat from surrounding will melt the ice. Okay, so now if you just use the heater only with the ice and then you on, right, this ice will melt because of heat from heater and also surrounding. So we want to minus the surrounding effect. So we want to minus the surrounding effect. So that's why you have the second set here. So this second set will show you the mass of ice. Mass of ice melted. Okay, because heat from surrounding. Okay, heat from surrounding. This one will be from surrounding and also from this from surrounding and also from the heater. Okay, surrounding and also from the heater. So what you do is you take this mass, you minus this. Okay, if you take the mass from beaker A minus beaker B, you'll get the actual mass, okay, of ice melted because of heat from the heater alone. Okay, from the heater alone. Okay, so we want to minus the surrounding effect. So that's why you have the second set here. Okay, so mass of ice melted because of it from surrounding. This one is because of surrounding and also because of the heater lah. So when you take this minus this, you get your actual mass of ice melted because of the heater. Okay, now okay, now so when we use this formula, right, we assume what? No heat loss to surrounding. That means what happened is all the heat from the heater, okay, is absorbed by the ice. Okay, absorbed by the ice lah. That is our actual. That is our assumption. But in reality, what happened? Some of the heat will be lost to surrounding, right? Some of the heat is lost to surrounding. Correct. So what happened is, in reality, right? Okay, sorry. In reality, some of the heat will be lost to surrounding. That's why when you do the experiment, right? When you do the experiment, you see that the value of L that you get is actually higher. Okay, the value of L you get is higher than the theoretical value. Okay, the value of L that you get will be higher lah. Why? Because you see, let's say lah, the heater supply 1000 joule. Okay, 1000 joule. So what happened? This 1000 joule will not be sent 100%. This 1000 joule is not absorbed 100% by the ice. So maybe out of 1000 joule, maybe the ice only get 800 joule. Correct. So 200 joule is lost to surrounding. So the ice only get 800. So that means the ice, okay, get lesser heat. So when the ice get lesser heat, what happened? The mass collected here also be lesser lah. Okay, the mass collected here will be lesser. That means the mass collected here will be lesser. So that's why the value of L is higher. Okay, that's why the value of L is higher. So what we must do is we must try to reduce the heat loss to surrounding. Okay, reduce the heat loss to surrounding. So that's why, right, what happened is for this experiment, right, you must make sure the heater is fully immersed in the ice cube. That means it must be fully covered with ice cube lah. Okay, that means your filter funnel has to be bigger lah. So make sure it is okay, fully covered. That means you have to submerge some more lah. Okay, you have to submerge some more. Submerge the thing into the ice some more. Okay, it's fully covered with ice. So all this is to reduce the heat loss to surrounding. Okay, if not, the value of specific diffusion is higher lah, larger than the standard value. Okay, so this is because what happened? Heat loss to surrounding lah. So the mass collected will be smaller. Okay, the mass collected will be smaller. Okay, so now we look at the question. Now, a head underwater electric heater used to boil water. What is the time required to reduce the mass of water by 4 kg after the water has reached the boiling point? Specific latent heat vaporization is 2.26 times 10^6. So this one you use Q equals to ml. Okay, so they give you power, right? So Q can be defined as PT. Okay, from the previous topic, Q equals to PT. So what is the power? The power is 800. So the time we don't know lah. So the mass is 4. This is 2.26 times 10 to the power of 6. Okay. Four times 6. Okay. So divide with 800. So you get, okay, your time will be 11,300 seconds. Okay, next. A 0.5 kilogram solid is heated by 100 watt heater. So the graph shows how the temperature of the substance varies with time. So calculate the specific latent heat. So this one you can use Q equals to ml. Okay, so Q is PT, right? So PT equals to ml. So your power is 100. Okay, now what is the time? So the time of melting, right? So melting only happens at this point of the graph. Okay, so melting, right? So melting doesn't start at 0 second, right? It started at 300. This is 300. This is 1050. So 1050, you have to minus 300. So the duration for melting is only 750. So this one is 750. And then your mass is 0.5. And then times L. Okay. So 100 times 750 divided with 0.5. So it'll be 150,000 joule kg minus 1. Joule kg minus 1. Okay, joule kg minus 1. Okay. Okay, now application of latent heat in everyday life, right? Okay, what happens is, okay, sweating actually cools down our bodies lah. So what happens is when we sweat, right? Okay, after that, what happens? The sweat evaporates. That means it will change to from liquid to gas. So in order to change from liquid to gas, you need to absorb the latent heat of vaporization. Okay, latent heat of vaporization. So what happens? It will absorb the latent heat of vaporization from our body lah. Okay, so that's why our body cools down. Okay, now drinks can be cooled down by adding several cube ice because same thing lah. So when ice melt, what happens? It will absorb latent heat of fusion from the drinks. Okay, so because of that, the temperature decreases lah. Okay, and then food can be cooked using steam. So what happens when steam condenses, right? Steam condenses, it will release latent heat of vaporization. Okay, it releases a huge amount of latent heat of vaporization. So the heat can be used to cook the food. Okay, can be used to cook the food. Okay, example of structured question. The solid substance of mass 0.1 kilogram is heated using 200 watt heater. A graph showing the variation of temperature with time. So based on the graph, what are the state of matter between point Wx, x, y, z? Y, z. So Wx will be solid. Okay, xy will be solid plus liquid. Okay, so yz will be only liquid. Now, using kinetic theory method, explain why at section xy the temperature remain constant. So why during xy the temperature remain constant? Okay, why during xy temperature is remain constant? So you can say heat is used to overcome bonding forces between molecules. Okay, or you can even say heat supply does not increase the kinetic energy of molecules. Okay, so heat supply doesn't increase the kinetic energy of molecules. Okay, so you can choose either one. Okay. Okay. Next, at yz, why the temperature increases, right? So what happened? The heat supply increases. Okay, the heat supply increases the kinetic energy of molecule. Okay, the heat supply increases the kinetic energy of molecules. Yes. Okay. Okay, some molecules. Okay. Next, using the graph, determine the melting point. So what is the melting point? So the melting point happen here, right? XY. So the melting point temperature refer here is 0. Okay, so the melting point will be 0 degrees Celsius. Okay. Next, the specific latent heat diffusion of the substance. So this one you have to use Q equals to ml. Change Q to PT. So PT equals to ml. Okay. So what is the power? The power is 200. Okay. Now the time is 2 to 9. 2 to 9. So the time is 7 minutes. Okay. 9 minus 2. 9 minus 2, 7 minutes. Okay. So the time is 7 minutes. So the power is 200. The time is 7 minutes. Convert to second. So times 60 lah. And then 0.1 times L. Okay. So 200 times 7 times 60 divided with 0.1. 840 joule. Kg minus 1. Okay, joule kg minus 1. Okay. Next, number 23. Now, diagram shows two sets of apparatus to determine the specific latent heat diffusion of ice. So, set A is not connected while set B is connected to the power supply. Okay, connected to the power supply. So, the question asking you lah. Okay, so what is the function of set A, right? So, set A, the function is to determine mass of ice melted. Okay, because heat from surrounding. Okay, so to determine the mass of ice melted because of heat from surrounding. Now compare the thermometer reading for set A, set B after 5 minutes lah. So what you can say, right? So during melting, right, the temperature doesn't change. Okay, so you can say the temperature is constant. Okay, constant can, okay, doesn't change also can lah. Okay, so name the heat involved. So latent heat of fusion. Okay, latent heat of fusion. Next, what is the amount of water collected in the beaker in set A after 5 minutes? So this is 200 gram, this is 180. 200, 180. So minus lah, so 20 gram. Okay, and then what is the mass of ice melted in beaker B after 5 minutes? Same thing lah, 380 minus 180. 380 minus 180. 380 minus 180 is 200 gram. So 200 gram lah. Okay, this 20 gram is because of ice melted. Ice melted because of heat from surrounding. This is surrounding plus heater. So the amount of water collected will be 200 minus 20. So 180 gram. Okay, 180 gram. Okay, if the power of heater is 200, calculate the specific latent heat. So this one you can use so Q equals to ml. So change this one to PT lah. So PT equals to ml. So the power is 200. And then the time is 5 minutes, convert to second. So 5 times 60. And then the mass is, okay, just now is 180 gram. 180 gram, convert to kilogram. 0.18. Okay, this one must be in kg. So divide with 1000 to convert to kilogram. And then times L. Okay. So 200 times 50 times 60. Divide with 0.18. L will be 333. Joule kg minus 1. Okay. Okay, number 24. Now, figure 3.1 shows apparatus to measure the specific latent heat diffusion of water. In this question, you may ignore the heat transferred to the ice from the room. The heater is switched on and water drips into the beaker at a constant rate in 2 minutes. So figure, okay, in 2 minutes, 31 grams of water drips into the beaker lah. So the power of heater is 85 watt. Okay, the power of heater is 85 watt. Huh? So calculate the amount of heat energy supplied by the heater in 2 minutes. Okay, so this one is the power. Huh? This is the time. So you want to find the Q lah. Huh? So we use Q equals to PT. Okay, Q equals to PT. Okay, so the power here is 85. So take 85 times with 2 times with 60. So 85 times 2 times 60. So we get 10,200 joule. Okay. Now use your answer to calculate the specific latent heat diffusion. So the mass melted is 31 gram. Okay, 31 gram, right? So this one we can use Q equals to ml. So this 10,200 31 gram equals to, so convert gram to kilogram, divide with 1000. So 0.031. Okay, times L. So L so 329,032 joule kg minus 1. Okay. Now in another experiment using the same heater, ice cooler than 0 degrees Celsius is used. State why less water drips into the beaker in 2 minutes. Okay, now you see if you use ice at 0 degrees Celsius, right? So what happens is, okay, so the process only involves from 0 degrees Celsius ice, you melt into 0 degrees Celsius water. Okay, so you don't need to increase the temperature lah. You just use all the heat to, so this one 2 minutes, in 2 minutes. Okay, so in 2 minutes you are using the heat 100% to melt the ice from 0 degrees Celsius ice to 0 degrees Celsius water. Now if you use ice cooler than 0, let's say you use the ice at temperature of -4. Okay, let's say the temperature of ice is -4 degrees Celsius. So what you're going to do is, first you need to increase the temperature first from -4 to 0 degrees Celsius. After that, then only you melt the thing. Okay, then only you melt to 0 degrees Celsius water. Okay, so that means what you must do is you need to increase the temperature first. So that means some of the heat is required to increase the temperature before melting. Like this one, right? You use 100% for melting. You're using this one 100% for melting. So for within these 2 minutes, okay, let's say the time here 2 minutes. So for within these 2 minutes, correct, definitely the mass of ice melted will be more because the heat supplied is used 100% to melt the ice. But this one, right, the heat is only used to melt the ice at this part. Okay, this one is used to melt. But before that, we use the heat to increase the temperature of ice. So that's why the mass collected will be lesser compared to this. Okay, so you can say some heat is used to increase temperature of ice before melting. Okay, some heat is used to increase temperature of ice before melting. Okay, so that's why the mass collected will be lesser. Okay, next. Figure 4.1 shows apparatus that could be used to measure the specific latent heat of ice. Underline the correct answer. So the heat absorbed during melting is known as specific latent, is known as latent heat of fusion. Fusion. Now explain why the temperature remain constant during the melting process even though heat is applied. So you can say heat is used to overcome bonding. Okay, process between molecules. Next, in an experiment, okay, 120 gram of ice at 0 is to be melted. Specific latent heat of ice 340 joule per gram. Assume that all the energy from the heater is used to melt the ice. So calculate the expected time for which the 60 watt heater is switched on. Okay, so that means you use Q equals to ml. So change Q to PT. So PT equals to ml. Oh, sorry, only PT. They already give you, oh, sorry. Oh, yeah. PT, Sorry, try 60 times your T. And then the mass will be, what do you call it? Okay, 120. Okay, and then the L will be 340. Now, for this question, I did not convert the mass to kilogram. Why? Because this one is gram, here also gram. They give you joule in gram. So no need to convert. Okay, no need to convert into kilogram. So that means your answer will be, so 120 times 340 divide with 60. Okay, so you get 640 seconds. Okay, so the time will be 680 seconds only. Okay, 680 seconds. Okay, next. Now, when the experiment is carried out, the ice melt in a lesser time than the expected time. So state one reason and then suggest modification, right? So why the ice melted in much lesser time? Okay, you see here. Now let's say this is your filter funnel. Okay, I make it slightly bigger so that you can see what's going on. So this is your beaker. So you put the heater here. Okay, so you have the ice here. Okay, so what's going to happen here is, right, here's your heater, right? So the heat from the heater will be used to melt the ice. So when you melt the ice, what happens? The size of the ice will be reduced. So the ice is going to become smaller, smaller, smaller. Okay, now you see there's an opening here. Okay, at the bottom, right? The opening at the bottom of the filter funnel here. See, what's going to happen is, our idea is, okay, we're going to assume that the heat, okay, the what do you call it? The ice, right? Need to be melted 100%. That means change to liquid 100%, then only drop into the beaker. Okay, then only start to flow into the beaker But in reality, this might not happen. What happens is, once the ice becomes smaller, that means the ice can pass through this opening here. Okay, it can drop, it can pass through. When it's bigger, maybe it cannot pass through. Once it becomes smaller, it can pass through. So what happens is, the ice don't need to melt. It will drop into the beaker. Actually, it haven't melted yet. Okay, but because the size is so small, okay, it can pass through the opening at the bottom here. So it will drop into here. So actually, it haven't melted 100% yet because the smaller size. Okay, so the ice can drop, okay, from the opening here of the filter funnel at the bottom here. Okay, so what we can do to reduce this effect, so at the bottom here you can put a wire gauze. So you put a wire gauze at the bottom here. Okay, so you put a wire gauze lah. So that if it is small, okay, it doesn't drop. Okay, it doesn't drop lah through the opening at the bottom of the filter funnel. Okay, so we put a wire gauze. That means it need to be melted. Okay, then only it will drop into the beaker. If not, even though he haven't melted, but because the size is so small, it can pass through the opening at the bottom of the filter funnel. So that's why you need to put a wire gauze here. Okay, so you can say why this happened, right? So small pieces. Okay, small pieces. Okay, so small pieces of ice, okay, can fall through the opening, okay, at the bottom of the filter funnel. Okay, so small pieces of ice, okay, can fall through the opening at the bottom of filter funnel lah. Okay, without being melted completely. Okay, without being melted completely. Okay, so how can we reduce this effect? Okay, you can say okay, put a wire gauze okay, at the bottom opening. Opening of filter funnel. Okay, or just put a wire gauze at the bottom of the filter funnel also can. Okay, so put a wire gauze at the bottom of the filter funnel. Okay, now number 30. Now diagram 4.1 shows a 0 kilogram ice is heated using 100,000 watt heater. So diagram 4.2 show how mass of ice M changes with time. So this actually is the mass of ice. It's not the mass of the water collected. Okay, so that's why you see the mass decreases. Because why? Okay, this one is measuring the mass of ice. Okay, so the ice will melt and then will drop into the beaker lah. So that's why the mass become lesser and lesser. So given the specific region of ice 334, right? Okay, what is the meaning of specific latent heat of fusion? So this one you can refer to this lah. Okay, so heat required, right, to change 1 kilogram of substance, right, from solid to liquid. Okay, from solid to liquid. Okay, next. Based on diagram 4.2, calculate the amount of heat absorbed by the ice during the melting. Okay, so you want to find the Q lah, Q. So this one you can use Q equals to PT. Okay, the power is 1000. Okay, now the time, right, the melting, right, it doesn't occur from 0 to 50 because 0 to 50, there's no change in your mass. So because why, right? Okay, the moment you on, right, So you need some time for the heat to be transferred from the heater to ice. So time is needed for the heat to be transferred from heater to ice. So that's why you see the temperature mass is constant for a while. After that only it start to melt. So it start to melt at this lah. Okay, melting start here. Okay, so that means your duration is 170 minus 50. Okay. So 1000 times 120. Okay, so 120,000 joule lah. Okay, 120,000 joule. Okay, next. Determine the value of X. Okay, so determine the value of X. So that is the answer for this lah. Okay, so that means what is the value of ice that is left? So first you need to know what is the mass melted. So the mass melted is Q equals to ml. Okay, so the Q is 120,000. Okay, the mass don't know. Now the value is 334. 334,000. So you can find the value of M. Okay, so divide with 334,000. So you get 0.36. Okay, 0.36 kg. Yeah. So what happened is, right? Okay, first you have 0.6 kg. Yeah. So this 0.6 kg is the initial mass of the ice. So what happened? The one melted based on the calculation just now, we get 0.36. Correct. So you have 0.6. So 0.36 has melted. So what is the value of X here? So 0.6 minus 0.36. So that would be answer lah. Okay, so the value of X, right? So 0.6 minus 0.36. So you get 0.24. Okay, 0.24 kg. So this is the value of X. Okay, that means this is the one left. Okay, this one left at 170 seconds. Okay, 0.24 kg. Okay, 0.24 kg. Okay. Okay, so next they ask you, give one reason why mass of ice constant for the first 50 seconds. So like just now, so time is needed. Okay, time is needed. Okay, for heat to be transferred. Okay, from the heater, okay, to the ice. Okay, so time is needed for heat to be transferred. Okay, from heater to ice. Okay, so these are example of question involving the concept of latent heat. Okay, so that's all for now. We will continue in the next lesson.